Okay, I guess we are live. Okay, um, let's start. It's 4:02. Fine. Hello, everyone, and welcome to the week 6 live session of the course Introduction to Machine Learning. My name is Rajvi Jain, and I'm a PhD student in ISC. So today's agenda is we'll discuss some questions, some doubts that were raised in the previous week's session, and we'll do some discussion on how to initialize better and what is the issue of reproducibility in machine learning and actually in all of science actually. And if time remains, we'll look at the week 5 practice questions and quiz questions. Okay. Um, all right. And as usual, what has been written will be uploaded in a PDF format, and the whole thing is being recorded and live streamed to YouTube right now. Okay. Good. So, okay. So last time, remember we were discussing something about this f of x equal to log summation of e power xi. Is it convex or not? So one idea was that can we look at it as some combination of convex functions, because e power xi is convex, right? And this we know because, let's say, the second derivative of this will still be e power x, which is greater than 0 at all points. So this is convex, but log as such is not convex, right? Because the first derivative is 1 by x, second derivative is 1 by x squared, which is less than 0 for all x, right? And hence log is not convex. So this particular if you write it as some combination of convex functions and hope that this would work, that's not true, right? So you need to use that approach that we discussed last time. I mean, one of the approaches is to discuss in this way. You can write it as SS transpose x greater than or equal to 0, right? Prove this, where S is the del f function, del f, the gradient of f, right? So try it out. Actually, has anyone tried this out, by the way? Any attempts made at this? No? Okay, so I'll say, just try it out. This is a really good proof. You will, have fun using even that Cauchy-Schwarz inequality, right? So, very good application of these stuff are present here. Okay, that was one thing. Second thing was why, in 0 less than p less than 1, the LP norm sort of equation that we had, a function that we had, why does that fail? So I'll not go into detail right now. It's straightforward from this Minkowski's identity. So I'll go to Wikipedia for this. You should be able to find out and understand exactly where things fail for this range of numbers, right? 0 less than p less than 1. Okay. All right. I wanted to have a deep discussion on this part actually. So one was that we were trying to understand the interchange of this min-max problem, the in-soup issue that we had, where it is possible, where it is not, and so on. So we'll do a bit of a discussion here, and hopefully this helps you understand this convex optimization a bit more better. Okay, so this is the problem statement that we have. Okay, that I want to minimize f naught of x. Okay, such that fi of x is less than 0, less than or equal to 0. Now we can add equality constraints here. We'll not do that for now. We can just in this whole proof as such, we can just look at with those constraints also. Just to make it simpler, I'm keeping it here like this. Now and let x star be the optimal x, right? And I'll say, okay, f of x star is p star, so p star is the optimal value that we want from this problem of optimization, right? And we discussed that I can create something called a Lagrangian, where I define it as L of x comma lambda, which is just a combination of the objective function and all the constraints that we have. With this constraint, lambda I greater than or equal to 0, right? I choose lambda i's to be greater than or equal to 0. Now let's look at a function g of lambda, which is defined like this, right? Minimum over L of x comma lambda over x, minimum over x, Now my claim is that this is less than or equal to f naught of x bar for all x bar in the feasible set. So any thoughts why this would be true? Why there are so many pings? Okay. So people who join new, fresh, the idea, the question is, let's say we have something like this, a problem for optimization, and we have the Lagrangian, right? It's straightforward with some lambda greater than or equal to 0. I define a new function g of lambda, which says, minimize over x, L of x comma lambda, right? So it becomes a function of lambda, and I'm saying that this will always be less than or equal to some f naught of x bar. Okay, this particular value will be less than or equal to f naught of x bar for all x bar in the feasible set. So any idea why this would be? Anyone can reason out why this would be? No ideas?
Hello.
Yeah.
Can we just invoke that since the set is bounded from above, there will be a least upper bound kind of thing. I'm just not confident about this. Just spit out some answer.
Okay. So yeah, we want to prove this lower bound thing. Okay, and then we'll go to the least upper bound and all of that stuff. But I'm asking a very simple algebraic question actually, that if you have this, if I define a function like this, right, I'm saying that this will be less than or equal to f naught of x bar for all x bar in feasible set. Okay, what does feasible set mean? What is a feasible point? Any idea what a feasible point is?
Any point that satisfies optimization
Constraints, correct? Yeah. So that means so this x bar, that means x bar, that is fi of x bar is less than or equal to 0, right? This is true because x bar is in the feasible set. Okay. Now I'm saying, okay, so what a lambda is? Lambdas are positive numbers, right? I mean, non-negative in some sense, non-negative numbers, right? So can I say that lambda I fi of x bar is less than or equal to 0? Right? Simple multiplication of a positive number. Now, okay, with this, let's say, with this in mind, can you reason out why this should be less than or equal to f naught of x bar? Look at the definition of Lagrangian.
Yeah, because it is non-positive.
Correct, right? So all of these, so I'm saying each of these individually is non-positive. Therefore, the sum will also be a non-positive number. That means that means something less than f naught of x, right? At x bar. So therefore, whatever I define here, whatever I've defined here, g of lambda will be less than or equal to f naught of x bar. Now, I'm saying that x star is the optimal x. Optimal in the sense optimal solution. So x star also has to satisfy all the constraints. That is x star also belongs to this feasible set. So therefore, I can write something like this. Does this make sense?
Yes.
Good. So therefore, what I'm doing is I'm saying that I'm saying I have a g of lambda function which is less than or equal to the p star. So I have basically constructed a lower bound on the optimal value. That is what I've done till now, right? And then the idea is if I try to maximize this lower bound, right? So my point is that g of lambda will be less than or equal to p star for all lambda, for all positive lambda. Very important, right? For all positive lambda. So therefore, when I try to maximize this g of lambda, what is the maximum I can reach? P star, right? So if I were to draw a simple graph here, right? Let's say this is lambda, this is g of lambda, and this is some value, it is p star, right? G of lambda sum goes like this, let's say. Okay, it can have whatever. Oh yeah, we'll discuss that anyway. So it's it has some curvature here, right? So my point is that I have constructed a lower bound on p star, that the optimal value of the function. If I try to find where this g of lambda maximizes, right, what can happen is I will reach some point which is either less than p star or equal to p star. right? So I can say that the maximum g of lambda that I have for for any best lambda star. So I'll call it as optimal lambda, right? Lambda star, and I'm giving this g of lambda star as d star. Okay, so what does d star mean in terms of all of this x and all, right? What I've done, I have maximized lambda with some constraints, where this is always true that I have a constraint lambda greater than or equal to 0, right? So I'm maximizing with respect to lambda which function, g of lambda. G of lambda is defined to be minimum of over x, L of x comma lambda. Until here, clear?
Yes.
Okay, so this is the definition of d star in some sense, right? The optimal dual function value that you will get. Okay, now let's look at this particular expression. So if I say I want to maximize with respect to lambda, which is greater than 0, L of x comma lambda. So what is L of x comma lambda? This expression from definition, right? F naught of x plus sigma I equal to m lambda I fi of x. Now I will claim that this is equal to f naught of x if this x is a feasible point. Otherwise, it will be infinity. Anyone want to help me understand why this would be true? So x is feasible. Okay, if x is feasible and lambda is positive, okay, what would happen if I try to maximize this function with respect to lambda? Lambda is I'm maximizing, not x.
So if it's feasible, it's a feasible point, then you will reach the upper bound, whatever is possible. Otherwise, you cannot claim any upper bound as such, right? When it's not a feasible point.
Correct. Because what I can do here is when lambda is positive, since all of these values are negative, right? What will happen? I'm multiplying again positive with negative. I get a negative value. This all is negative. So when I'm trying to maximize with respect to lambda, I can take this lambda any high, any low, whatever. I can never cross f naught of x, right? For feasible points.
Yeah.
That is important. For feasible points, I will never be able to cross f naught of x because this will always be negative. So this is true. If even a single constraint I violate, right? Let's say there is some constraint j, which a point x is violating. That means what? F j of x, let's say I'll call it x tilde whatever, right? Let's say this is greater than 0, right? So what I can do is I can choose lambda j, right, tending to infinity, because see, I'm trying to maximize. I can choose any lambda such that lambda should be more than 0. So I can choose lambda infinity also. If I choose infinity, immediately this whole function goes to infinity, right? So this particular maximizing with respect to lambda with the constraint greater than 0 basically gives me either f naught of x or infinity. Okay, now let's say I want to minimize. I'll put this minimizing operation on both the sides, right? I'll say minimize with respect to x, this guy is equal to minimizing f naught of x with respect to x. Why? Because if I'm minimizing, infinity will never be a possible solution, right? So it is just like saying I will be minimizing f naught of x, which we already know is p star. Correct? Is this idea clear?
Yeah.
Right? I'm just putting minimize the operation over on both the sides, and therefore if I have strong duality, this thing starts holding. Strong duality tells that this gap, right? Let's say this is d star, right? As we discussed. So if d star is equal to p star, that's strong duality, right? D star by definition we got like this: maximize outside first, maximize with respect to lambda, minimize x, L of x comma lambda. And p star we just saw the definition: minimize with respect to x, maximize with respect to lambda, L of x comma lambda. Okay, so if strong duality holds, this is true. Otherwise, what will be true? We know that d star will be less than or equal to p star, right? Because d star is g of lambda's maximum value, and we know g of lambda will be less than or equal to p star always. So therefore, I can say if I have weak duality, what happens is this thing becomes true: minimize L of x comma lambda strictly less than Okay, this is the idea. This is in weak duality. In strong duality, sorry, this is in general. In weak duality, this we lose the equality. In strong duality, this becomes strict. We say that it is exactly equal. Is this sort of helps you understand what the confusion was from last time?
Yeah, things are a lot more clearer now, at least to me.
Good. Okay. Good. So so this
So
particular.
I just wanted to have a little question. So basically, in duality, what you are doing, you are transferring the optimization from x to the lambda, right? Whenever you are bringing in lambda as a Lagrange multiplier, am I right
Yep.
in saying this?
Yep, correct. Yes, it's exactly what we're doing, right? We are trying to shift this, working with this x, which has so many constraints and everything. What we're saying, okay, I will not look at that. I will shift to a dual formulation where I work with lambdas. Now, the biggest advantage here by doing that is that g of lambda, this operation, this problem of maximizing g of lambda, this is all g of lambda is always a concave function, right? So you're maximizing a concave function, you will have, so this particular space that you have, this lambda space that you have, you will always have a one single maxima, okay, which you will be able to find, right? And once you have that, and so therefore you have like a, in some sense, like a proper solution in place, right? And then you can look at how I'm doing with respect to duality. I mean the actual optimal this one.
So the duality makes the problem much more tractable, right? In a sense.
Correct. Yes.
Okay.
Yeah.
Thank you.
Yeah. Okay. And then so in case you have, in some sense, if you can estimate what P star would be and all of that, again, that's a very different thing to discuss. But the idea is that, let's say you look at this difference, P star minus D star. Okay. If it is very high, you say that, okay, this duality solution is not good for me, right? You can say, okay, this is not good for me, and I'll use some other method, right? If it is, if the thing is very less difference, for example, with respect to what tolerance you have, so you'll say, okay, I will not do the P star sort of optimization. I will use duality because there it's much more tractable, and I will do that. That's the idea.
Okay. Yeah.
So if it is large, you look for alternate methods, and if it is small, you accept the dual solution as your optimal value, right? Okay.
So if it's large, so you have to resort to some other solution methods like interior point methods and other things, right?
Yes. So you have to look at some other methods to solve this problem. Correct.
Okay.
Yeah. Okay. Good. So then this is the idea of this why you can exchange in SOAP sort of thing, and mainly in case of strong duality you can actually interchange and it becomes simpler to solve. Now so actually speaking, we should use this idea of inf and SOAP, right? Because what they mean is that in case the maximum is not reachable, is not attainable, then we should use the word of SOAP. SOAP is basically talking about, if I'm not wrong, it's
supremum and infimum.
No, it's the greatest lower bound, right?
Supremum is supremum is the greatest lower bound. Infimum is the greatest lower bound is the infimum. And the least upper bound is the supremum.
Yeah, least upper bound and greatest lower bound sort of thing, right? So this is the idea. So for example, let's say if I ask you a question, what is the maximum of tan h function over x, right? Now the thing is, the maximum of tan h we know it is 1, right? But when is that reached? It is reached when tan h of infinity. Okay, but the thing is, we don't consider infinity generally speaking in our work of this one, right? So in some sense, this maximum, if x belongs to R and R doesn't have infinity, by the way, so this is not well defined. You cannot say what is the maximum value of tan h, because this can keep on going towards 1, right? But SOAP exists. You can say SOAP x belongs to R, tan h of x, right, is exactly 1, because we are saying that the lowest upper bound that this tan h function can take, it will never cross 1, which is what we are saying with respect to SOAP. Now can you reach the upper bound or not? That's a different issue. Okay, so ideally we should use SOAP here, because that will become more relevant when you talk about this sort of a formulation, right? Because there's no guarantee that the maximum will reach this f naught of x. So ideally I should use here soap and use soap in everywhere. But you can look at so this all of this is actually present in Convex Optimization by Boyd. This is the book, a really good book. And with respect to the thing that we discussed today, it's in chapter 5, and specifically these sections. So in case you have more ideas on what you want to see something about something more, you can look at in this chapter for this book. All right. Okay, so this is I wanted to discuss about this issue that we had last time. Now there are two things pending. One is this k2 of x. Sorry, this was that k1 of x is a kernel which has x and x squared. K2 is a kernel which has 3x and 3x squared. So we wanted to prove that the margin has become thrice. So we went through intuition and proving it mathematically. I found a solution in some sense, and we'll discuss it next week. There was one more thing about assignment solutions. You guys wanted these solutions to be posted in this one. So the thing is, the course TAs have given it to the NPTEL people, if I'm not wrong. So it's just that the NPTEL has to release it on the web pages. So I've sent them out a mail. We'll see where they are with the request. Okay, so this is the previous week questions that we had. So we'll go to something regarding the weight, how to initialize weights in neural networks. Okay, so the first thing was, as discussed in class, right? The simplest way to initialize weights could be just use zeros or some same value in some sense, right? Now when you use zero weights, what will happen, right? All the outputs are actually going to be zeros, right? Because what you actually compute in any run is something like this, right? You're saying sigma over j, wij xi, whatever, right? So this is right, over I. Okay. So if there are zeros, then all the outputs so basically every neuron is going to give you the same value, which is 0, right? That is the summation. And then what will happen is your weight update equations, if you look at it, right, you will have some term like this when you're updating your weights, which goes like, if I'm not, I don't know if you're using these notations actually. So delta I talks about what is the gradient that has come from the previous layer, right? And this will have a term which has wi multiplying something else here, right? Some x or whatever, right? So what will happen is the gradient which comes to the previous layer is also going to be 0. If that is 0, what happens is there is no update. If there is no update, the weight remains at 0. So basically your model will not learn anything. It will just remain at the same error level. Okay, so hence zero weights don't make sense. So if you want to go through it more cleanly, I would suggest looking at the equations and putting wij equal to 0 for the last layer, the previous layer, and so on, and you will see that things start becoming useless after a while. Now the thing is, so can't we use the same value for all, right? Let's say I will initialize, this is the first condition. If I use, let's say, initialize wij of all layers or whatever equal to some k value or whatever, right? So what will happen is, now in this case, let's say I have some architecture like this. Okay, so what is this node computing, right? After all, it's computing, let's say this is L I N J, something like this. Okay, so this is basically computing some activation of W, let's say Li x L, okay, over L. Now so what will happen here is you will get, since this is same, you will get k times sigma xl, right, which is the same value, which is a value which these guys will also compute. This one will have the same computation, same value will be computed by these guys. Then you'll have the sigma over this, I mean some non-linearity over this, right? So the value, so this guy, the last layer, I mean the output layer, whatever this computes, will also be again something like, let's say ij, and output of the previous layer, let's say the yi is same for all, wij is same for all these three, right? So some constant value is going to come, right? Let's say I will call it as some m, right? Now, when you back propagate, you will actually see that the weight updates are, so the gradients are non-zero. That is true. Okay, when you plug this all in the equations, you'll see the weight update will happen. But the weight update will happen in such a way that all the weights will have the same update. Right? So the next iteration, every weight will have some new value, but every will have the same, some n, right? So what is going to happen, right? Every time you do this update, it's going to remain. So all of these guys will update to the same value. There is no change in the output that is coming. I mean, there's nothing changing between these neurons. All of them are doing the same computation. So basically, it's just you're wasting the computation resources of your network. And let's say, in case the solution required you to have different weights. Okay, for example, there was some function that you were trying to model. Let's say some sigma of the actual, let's say the target function y, right, which you want to predict, right, was actually some function of your input and some weight and something, but these weights were different. You will never be able to model it, right, just because of the fact that all your weights have the same updates. So these are the two reasons why this all same also won't work, right? So you'll have the same output for all the hidden layers. You'll have the same weight update to all of them, and therefore you're just doing the same calculation over over different neurons. The same thing is being computed. That's one. And second thing is, you will have less representative power. The whole idea of neural network is that you should be able to model any kind of complex function, right? But by doing this, you're actually limiting the power of neural network, and you will not be able to get good results, right? This is the idea of this is the issue with having all same weights initialization. Okay, fine. So this is so now we know that we should not have the same weights, we should not have zeros, whatever. So next best, what you can do, right? So I'll say, okay, I will use some uniform random variable. And we also already discussed in the lecture by sir that we want to stay in that linear region of your tan h or your sigmoid sort of a function, right? So I will do something like so close to 0 you will initialize. Let's say, for example, minus 0.05 to 0.05, right? This is some uniform distribution over this range, right? 0.05 to this one, right? So now the question, so then people had question like, why only uniform? Can I not do Gaussian distribution? I'll take n of 0 comma 1, right? 0 mean and 1 standard deviation. So can't I do that? And why only these two? I actually have so many other different ways of choosing doing randomization. So why only these two, or are there any properties that we can look at and see whether this like which is better in these two and so on, right? So with that in mind, we'll look at one tool developed by this deep learning AI platform, where you can look at some input examples, okay, and change your the way you initialize your network, and look at how your cost boundary is going. Okay, I mean your boundary of the plane is going, right? So let's say we look at 0 and I start the function. Okay, so as you can see, the loss is not changing at all, right? There is no change in the loss, and you can actually choose to see either the weights or the gradient. So weight, you can see they are yellow, like they are staying in 0 only, and this there is no change in the output, I mean the decision boundary, right? Or you can look at the gradient also. The gradient is also 0 basically, which is exactly what we discussed, right? So that's one thing that I wanted to show you. Then let's say you look at two small values, okay, very small. What will happen, right? There is some changes though, but not good enough, right?
I think there is no changes. There are no changes because the cost function isn't changing.
Isn't changing, right? So too small. What is so okay? So what is happening here though?
Yeah, now it's changing.
Now it starts moving. So what's happening here though? So why do you think too small causes an issue like this? So which part of your equations of your neural network can you think of where this is causing an issue? Any ideas?
The gradients may be too small for it to update
For it to update,
over each
right?
iteration.
Right. So when you have, for example, sigmoid function like this, right? 0 and 0.5, even tan h for that matter, has this saturation property sort of thing, right? 0, 0, and this my. So what happens is when the values are too small, um, right? So too small in a sense. So this literally zero update that's happening. For example, this is the gradient of your what do you call that, sigmoid, right? When the values are too small, they're somewhere here, right? Or yeah, somewhere here, right? So you're multiplying your weights with x, your input, and all of that. So since the weights are so small, your inputs multiplication is not able to bring it to a good place. So the gradients are actually very small. So it takes a lot of time for the network to actually come to some the thing is, it is learning something, but the learning is so less that it takes time for it to show up in a good way for the thing to look at, right? That is the thing that is happening here. Okay, so let's look at the gradient actually.
But
Let me just restart.
eventually it will take off, right?
Eventually
Eventually
it
it
will
will
take
learn
off.
something.
Correct. Eventually it will take off. Now if you see here, the gradient is actually zero in some sense. Very, very small. Like it's not doing anything literally. Right? After a while you should see something start going up, right? So this is the in some sense the issue, right? If you choose very small weights, it can cause your learning to happen very, very slow, right? You'll have lot of updates to your weights, right? Because here each epoch is one update, is one weight update, but the weight updates are not good enough for the network to learn anything for a long, long time, right? That is the idea here. Okay, and see, you might not feel it's a big thing right now. Okay, okay, but I'll stop for a while. You can see like some things are now updating, right? See this thing has improved a bit. These things are improving. This guy has tried to go to positive. This is going towards negative, like that. And now you should see some change here. I'll keep it on, whatever, right? So the idea is that you may not feel like, okay, it's too much of issue, right? If I have too small also, it's fine. I'll just wait for a while. You should understand that this is a very small network, right? If for example, let's say you have like a resonate sort of a thing where you have like some 20 layers of a neural network, and so having too small initialization will actually, you will have to wait for a long, long time, right? And those big networks are actually run on GPUs and stuff. So your GPU is just doing very small calculations over and over. You're wasting the time of training, right? So this is also not a good idea to have very small initialization weights. Okay, that is one. Okay, second thing we'll look at is too large weights. Any idea what will happen here?
Yeah, it will saturate the network outputs.
It's actually network outputs. But I was thinking that it could also, start putting your, I mean, yeah. So what will happen is you start going in this region of your gradient, right? Where again the learning is very small, right? And we'll look at that once. So the learning is very small. It's almost in the same range of cost functions, right? And it might take a while for it to recover, right? So this is the issue with too large. So it's sort of the same issue, that what has happened is now we are in the region where the gradients are very small because of the large weights. Your sum has your input to this activation functions has gone very high, right? So your gradient at that particular point is very, very low. So the network is not able to learn much from that. And yeah, I think it'll take a while for it to fix. Anyway, so I'll just just go through it. You can run this. I'm putting all these links in the Jamboard, so you get the links, and I suggest try it out with different data sets and stuff like that. You'll be very glad to see such things happening. Okay, and let's see what is the gradient actually. So see, almost all of these layers just have 0. Literally nothing is passing back to the initial layers at all, right? And yeah, this this is a very weird sort of this one. This particular weight, the gradient is changing rapidly. It's going to positive negative, and so on, right? Okay, these are some weirdness that is happening. Okay, let's look at the if you have appropriate this one, appropriate in quotes.
Raj, I had a small question. So the decision boundaries here are quite different from the previous case. So will it generally be the case like those? The decisions boundaries when the gradients are very high or very low, in either case they will be different, or will they converge to the same result? Any general suggestions on those?
Sorry, what?
Means when you showed us two idiosyncratic cases, right? When
Right.
it was too large and when it was too small.
Mm.
So the decision boundaries learned in those two cases are very different.
Correct.
So will they ever converge to a same decision boundary? That's my question. If we let it run long enough, if we let the network run long enough.
No. So it's possible that it may not learn the same decision boundary. Yes, that is true, because these are all local minima sort of issues, right?
Yeah, local optima, right? Yeah.
Local optima sort of issues. So it's possible that these should the two boundaries that you learn at the end may be very, very different, right?
Yeah,
which is why
okay,
it makes that big of an effort is going in machine learning to understand what is actually being learned at each neuron and at each layer, right? You're trying to so how do you interpret what the model has learned, right? So that is a very big problem space in itself, right? Okay, so the idea of local minima, so it's possible that you will have very different decision boundaries. Okay, so with the appropriate thing or whatever, so you can see that there is a good learning curve. You can see that cost is decreasing gradually at every epoch, and respectively you can see how the the space in the boundary space changes here, right? So this looks like a good loss curve, right? So ideally you should see that from the initial point itself, you should have like a good decrease in at every epoch, right? Again, these are very clean data sets in some sense. In reality, it may not be that way, but you should be able to find out where your ML algorithm is overfitting, underfitting, and stuff like that. And I guess that's covered in detail by survey, when you can see your loss functions and try to understand where it is underfitting, overfitting, and stuff like that, right? This is so this basically drives home the point that that we need some sort of appropriate way to have your weight initialization, right? So this brought about some questions in the literature that so then what do we do, like what else can we think about, and can we somehow sort of formalize this idea, and can we look at something a bit more than just empirical stuff. So this paper by Xavier et al, they sort of tried to formalize this idea in the first place, and they came up with some heuristics, and they looked at what should work, what shouldn't work, and stuff like that. So I'll suggest that go through this particular link, and you will see some very basic sort of a math again, which is mentioned here. So the idea is that one way to initialize networks when you have sigmoid or tanh sort of activations is to using something called as a Xavier initialization. Okay, Xavier initialization. So the idea in Xavier is that you will initialize them with something like this. So we saw that n of 0 comma 1, that is your Gaussian distribution, your of 0 mean 1 standard deviation. What they said that okay, 0 mean is fine, but you need to make your variance to be 1 by nl minus 1. Here nl minus 1 means the number of hidden units in the previous layer, right? So for example, if I have a network like this, what I will do is these weights will have the variance among them to be 1 by 2, because 2 is the number of previous layer weights. the weights here will have the initial variance to be 1 by 3. Okay, and the biases in all of these areas, because I also have a bias term, right, here. Each of these neurons have a bias term and stuff like that. So those biases are set to 0. So if you do that, what happens is you don't have this sort of a, I mean, you do much better compared to just using your uniform distribution, or Gaussian distribution, like that. Okay, so I'll suggest to go through this math. It's a very, very simple math here, regarding some one probability idea of what is the variance of independent random variables, what is the mean of set of random variables, how are they related, and then that basically is the idea of with that you'll be able to understand how this particular thing makes sense. Okay, so in that way, I'll just show you one last item. Yeah, where do I have to load it. Okay, so the idea here is that when you use Xavier initialization, so over the training process and your output process, what happens is your activations. Sorry, my mistake. Not the weights. The activations. The activations that are produced, that is your sigma wi xi. Let's say the weight and the x, the input to that neuron. That particular sum, that is the activation. Those activations should have similar mean and similar variance, right? So this is the mean, for example, 0 everywhere, and they have similar variance across them. Okay, that is the idea in Xavier sort of a method. Okay, so I'll suggest you just go through this particular this website, try out different things here, and just have a small look at the math here. Okay, so we have and actually speaking, then we had things like new things came up which were like ReLU activation function. I hope you have been talked about ReLU function. There was one more new which came out called CeLU. Okay, which was a scaled exponential linear unit. The theory behind CeLU itself is very, very strong and very, very good to understand why CeLU works in some places and stuff like that. So each of these, so then people asked, okay, then what is the best way to initialize the weights if I'm using ReLU activation function? What is the best way if I use CeLU activation function, and so on? So people have spent like a lot of effort in trying to understand what is the best way to do this, and from there is where you choose a good way to initialize a neural network. The idea being that you might be able to find a better minima. That's point number one. Point number two, you may not at least try to overfit, which is the idea of how to have better weights to be initialized. Okay, so that is one thing that I wanted to discuss. Second thing, was that let's say okay, so have we discussed like batch size? What should be like where is batch size comes into picture? What is a good batch size? Have you discussed something about this in the course?
No, batch size is not discussed, I presume.
Okay, that's not fine. So at least in the way you do it, the way these loops, I mean ML things will be done is, for example, let's say you have some sort of a one loop for epochs, right? The number of times you want the ML model to look at the whole data set. Okay, for example, let's say some for loop on the epochs that you have in place. Generally, this is kept to a very high value, like 1,000 or something, generally speaking. And then you so ideally what you want to do is you will say take the whole neural network, take the whole data set and train on them and keep on updating, right? So what you will do is you will say, okay, run the your neural network, right, with the data. Okay, so whatever you got the output, you will back propagate this, right, and do your weight updates, right? And then what you will do is you will have some sort of a measure to check if I have converged to my minima or if I've converged in some sense. So it could be based on loss, it could be based on some metric that you have. For example, you want to look at how is my accuracy changing, or how is the correlation coefficient changing between my the predicted and the target variable, and some stuff like that, right? So you can have some sort of a measure to check whether you have a converged or not, right? Is converged sort of a question here. If it is not, you'll continue. Otherwise, you'll say break from the loop, and you'll say, okay, I'm done with my training. This is fine. This is a way to, one way to do it. The other way, at least the way your stochastic gradient descent. So this is the gradient descent idea. So what stochastic gradient descent tells you, right, is that I will go through each data point. Okay, I will say for sample in data set, I'll have one more loop here. I will run the neural network for this particular sample. I have some output. I will back propagate that particular output, that particular error. I'll update the weights for that particular sample using that error that I have. I will do this for all samples in the data set. And at the end, after I run through the whole data set, I will ask this question, is converged or not, right? So I'll have some metric to look at the epoch level. I'll have some metrics, right? And say whether I have converged throughout my epochs or not, right? This is the stochastic gradient descent approach. Okay, so ideally, so the reason it's called stochastic is because it sort of looks at one sample, and you have some other properties there, right? So and ideally what you do is, you here, before you run this thing, what you'll do is you'll shuffle the data set. Okay, you don't want your model to look at the order of your samples to have the same sample, same order of your data samples every time it runs its updates, right? So what you do is you shuffle the data set and then run your samples. Okay, now there were issues with this previously. The thing was that if your data is very large, okay, what happens is that you will not be able to fit this in memory, right? So you'll have RAM issues. Okay, so then the point was that, okay, but the thing is, this is the best thing to do, right? Why? Because your estimates that you get for the gradients, those are the best, because you're looking at the whole data set at once. Now here the idea is that if I do it in this way, and if I do it for enough number of epochs, what will happen is, so here the issue is that your gradients that you get are noisy. Why they are noisy? Because what has happened is, you're looking at one sample, right? So let's say if you have one sample which is very bad, it will just push your weights to some other region altogether, right? And if it is good, for example, it keeps shifting your weights, your weights in very different directions. Okay, so that can happen. But the thing is, this will fit in your memory, because for sure, I mean, we're hoping that we have at least some memory to fit one sample in the memory, right? And then, okay, so but the issue is, it's very noisy gradients. So we don't have good gradients. So what will happen is, you need more number of epochs to finish up your convergence. So it'll take time to converge. Here you don't have space, which is your classic space-time issues, right? These are always anti in some sense. So people said, okay, we will use something called as mini batch. Okay, so or batch in some sense, batch gradient descent. The idea is that I'll have the same loops for epochs, let's say some epoch loop. Now I will divide my data set into batches with some batch size. Okay, so divide data set into batches, right? And then run a loop across the batches. So for batch, you will run your NN with the batch, right? And then you will back propagate. So you will do one weight update per batch, right? And then at the end of all the batches, you will look at the question of is converged or not. Okay, this is the idea. And obviously you will shuffle here before converting into batches. Okay, so this was the some sort of a trade-off between these two, right? Why? Because this gives you obviously better, if you have smaller batch, you'll be able to fit that much data into your memory, into your RAM, and work with it. That's one thing. Second thing, they won't be as noisy because now your gradients are, you're looking at the gradient for a for some samples which is more than just one, right? So you have better gradients in some sense, better gradient estimates. Okay, so now now came the usual question: what is the batch size, good batch size to choose? Okay, so people, again, this is not very well answered question. You generally actually choose this this is basically a hyperparameter, and you see how much can fit in your RAM. That becomes your maximum value that you can try, and the minimum is obviously one, but one is not suggested because obviously, as we discussed, it can keep on shifting a lot, right? So to drive home the point of this batch size and stuff like that, you can look at this particular website where you can try out different batch sizes and stuff like this. So I can change my initial point. For example, this is a data set that you have, that you want to fit your model with, right? And the model has just two parameters, W and your B, that is your intercept and your slope, right? So you can always do this using linear regression. Now the point is, if you wanted to use gradient descent on this linear regression sort of a problem, right? How would you go about doing it, and what looks like would happen in case you try different things? Okay, that's the idea. Okay, so before we go to the visualization, have you discussed about learning rates? How learning rates, how should you choose learning rate, and what happens if you have high, low learning rate? Any idea? Have they discussed this idea of learning rates?
Yeah, learning rate was discussed
Okay.
to a certain extent in the class.
Okay, should you choose like a low learning rate or high learning rate? So what is the trade-off for learning rate in some sense? So what will happen if you use low, like very small learning rates?
Converge very slowly.
Converge very slowly, right? So slow convergence is the issue. So you need lot of time. You need to you will have a lot of weight updates, because so convergence in the sense in terms of epochs. So you have many epochs, you have many weight updates. So it'll take time for it to converge, right? And what happens if it is very large?
It may overshoot the optimal point.
Right, overshoot optimal point. So basically you need some sort of trade-off in this case, right? So okay, so you should basically choose some sort of a medium learning rate. Now this is also again not a well-defined problem to solve. It's all just tuning hyperparameters. So but there are some ideas in learning rate. I'll discuss a few of them, one of them here, and then we'll close this discussion. So we actually have some sort of you can visualize how the weight space, which is your in this case two values, which is your slope and intercept, how it is changing with respect to different epochs. Okay, and you can see here, the cost will be what? Cost will be a function of these two, weight and bias, right? So it's actually a 3D graph. So what we're showing here is the contours of that 3D graph, right? So all of the values, all of these weight and bias values of this particular oval shape have the same cost function. Okay, and the optimal is somewhere here. This is the ground truth, right? Using which they generate this data set, right? So okay, so we look at two small examples, and then we'll see that what to do. So I'm choosing basically a medium learning rate, which is what our intuition tells us, and I'm using a very small batch is exactly equal to 1, right? So if you see here, what is happening, right? So basically when I use small batch size, my gradients are not very clean, right? They keep on shifting because each whatever point I chose one point, right? For example, when I choose this point, when I choose this point, right, each of them keeps shooting the weights in one or the other direction very strongly, right? So hence what will happen is you'll have a loss function which looks very bad in some sense. Like you basically have like a too much jitter in your loss function and your basically your weight space, right? So it can become a bit of an issue in reaching your ground truth, right? So let's say if I use both medium, some 24 points here for example, right? So it is a bit better, right? You have some better movement which is happening here, right? It's not as shaky uh, as it was when we had one batch size, but the thing is again not very smooth, but it's doing the job what it has to do, right? And if I use the whole data set, let's say my RAM is strong enough to fit all of these data points, so that is the best in some sense, right? So it's a very very clean sort of a going to a movement towards the optimal point. Okay, so that is one idea that I wanted to show. Now we'll see what combination of this batch size and learning rate is okay, right? If I want to use a large learning rate, let's say if I use a large learning rate, which batch size do you think is better? Any thoughts?
Large should be better, right?
A large batch size, you mean?
Yes.
Correct. Why?
Yeah, because large learning rate means a single misdirection would change the direction to a large extent, right?
Large
Of a
extent.
stochastic gradient.
Right, correct. So we can visualize that here. For example, if I'm doing this, it is just like based on what point I chose in what order, let's say, when I'm training the neural network, it keeps on shifting here and there. Your loss function is just crazy, right? It's oscillating.
It's chaotic, right? Yeah,
Literally
dynamics is chaotic, right?
It's literally chaotic, right? And you actually have no guarantee that you will reach the optimal point, right? See, you so hence this is the sort of things which make ML difficult in training, right? Because if you do something wrong, you will not even understand what is going wrong. So you need to depend a lot on heuristics and a lot on what the people have worked with and tried to figure out with their experiments and stuff like that, right? So hence this is obviously a very bad example, right? So large learning rate, if you have, you better to not have a very small batch size. Let's look at this guy, right? So good. So it went towards the optimal point, but you can see the initial shoot up, right? Ideally speaking, it shouldn't have gone that far also. When you, for example, come here, ideally the direction for update should have been something like this, right? But now because of large learning rate, it shift from here, it just shifted to some other area and then fixed itself and coming back here, right? But still no sort of a convergence in some sense. If you have it's still shifting very badly. Let's say if I use this guy, MB equal to this one, so this is much better, right? Much better. So though I have a large learning rate, if I can counter it in some sense with a large batch size, I'm still okay, right? So if for example you have a GPU which can handle like 48 GB data and you have like images which are for example ImageNet data set where you have like colored images and you have like so three-dimensional channels and so many values and stuff like that. So in case you're able to fit a lot of it in your memory, you can go ahead with large learning rates, right? Because that will actually make your it'll make your update to be very fast towards the optimal, right? And the only reason for that is that because you have good very strong and very good estimates of your gradients. Because I'm using the whole data set, I have very good estimates for my gradients, and therefore using a large learning rate is fine, because I know with much some sort of confidence that this direction is very good for my loss function, and so I can take a large step and I'll still be okay with going there. Okay, that's the basic intuition you should remember in terms of large learning rates. Okay, so we look at one example of small, and this is very sort of thought process very clear that if you have small learning rates, though I'm using the whole data set for example, right, I still make very small updates towards my optimal point, with the only reason that so a small learning rate tells you that I'm not so confident, so don't take a large step, take a small step, right? And hence you're losing out on this idea of though you have the whole data set, you're not able to make good use of it, right? So very small learning rate, not good. Very large learning rate, if you want to use, make sure you have large batch size. Medium learning rate is better in some sense. Okay, is this idea clear?
Yeah, nice presentation.
Yeah, I know. this so basically
This is what the
this
interesting thing starts.
correct, exactly, right. So you have the data, you sort of think about some architecture, and this is where things start actually breaking and actually not working out, right? You need to think about all these hyperparameters also, to make sure that you have a good result from your ML model, right? Okay, so these are some things I wanted to show you, and you can play around here. There's even more stuff in this particular website. I won't go into much here. So you have like which optimizer is better, Adam, gradient descent. You have so momentum is basically something which uses this second order information about your loss function, right? So some sort of a second gradient, for example, Hessian sort of a thought process, and so it'll use that also in its computation of your step, right? So that's one, and I guess that's the end of it. Okay, so that's the idea of this one. Okay, so I'll briefly touch on one good point that I read recently. Oh, we're already at 5, is it? Okay, sorry, I'll just take up 2 minutes. It's a good issue to think about. So let's say I have this loss function. Okay, convex, this is fine, good. You have a minima, you have a stressed single minima and everything, that's good. Now let's say you reach somewhere here in your working of your weight. Let's say this is a weight axis, this is a loss axis. Now because of the learning rate that was there, let's say you end up choosing a large step which puts you in exactly the same loss but on the different side of the weight of the optima, right? And when you're here, you again choose the same, I mean with the same learning rate, and this brings you back, let's say here. Okay, now I'll ask you a simple question. What would this look like in the loss versus epoch curve? What would this phenomena look like?
Loss curve wouldn't change, right?
Wouldn't change, right? So let's say if I'm looking at the epochs here, okay, and this is a loss curve, right? So okay, let's say you did some good training, you had very nice learning rate, you reached some bad point, you reached here, which is a good thing, and now what will happen? Your loss will just remain as it is, right? So people figured out that this is happening because so in some sense this was what is happening in their problems, right? So what did so one heuristic in some sense is that you have a changing learning rate, right? Changing learning rate. So what you do here is you say, okay, has it reached a plateau, right? There's no good change in the loss function. If I have reached a plateau, I will reduce my learning rate by some value. Okay, reduce learning rate. For example, I make it 1 by 10 or of the current value, right? For example, if it was 10 power minus 3, I'll make it 10 power minus 4 and then continue my epoch, right? So will this help in this scenario? By making it a less learning rate?
It should help, right?
Yes,
because then it will reach a different point of the object loss curve, right?
Correct, right? So this step is now made very small, so it actually moves something like this, right? And hopefully it will now reach the minima in a better hopefully it'll reach the minima over which it was oscillating in some sense, right? So this is actually the idea of reduce learning rate on plateau sort of a thing. I think this you will see in many famous common ML libraries. Your TensorFlow, PyTorch, everything supports this sort of approach where they look at learning rates and if it has reached some sort of a plateau, now your learning rate will actually go down, like some more go down, right? So that is one approach that you can take to make it some sort of an so your learning rate need not be always a fixed quantity. You can change the learning rate also over your epochs, right? There's another idea recently, I think it came out, was that where the authors propose something like this. They say, don't change your learning rate when this happens. Okay, you increase your batch size. Okay, increase your batch size, because now what happens is, so keep the learning rate same, but now what has happened, because of your increased batch size, you have a better estimate of your gradient, and hopefully you will do better. Your direction would change, and you might reach a better minima. Okay, so see, the idea of batch size is always get better estimates. If you increase the batch size, you get better estimates of the direction. There is a gradient, right? Learning rate sort of tells you what should be the confidence in your gradient, right? With what confidence should I work, right? That's the idea. Okay, so instead of saying you decrease the confidence in the estimate, I'll say keep the same confidence, but by making sure that I'll get you a better estimate of the gradient by increasing my batch size. This is also another idea which has come up recently. Okay, so this also you can try to sort of do in your real life projects. Okay, fine. So we'll sort of stop here. So basically, I just want to tell like a lot of ML papers or results that you see are not reproducible. For example, your algorithm and your data, if I use and try to run on my machine, I'm not getting the same results. Now that is a very bad thing. So I think about why it's a bad thing, and I given some steps about how to make it reproducible. How can the other guy, how can the other person also get the similar results as what I got? Some ideas here. Just go about it, and okay, we'll close the session now. Any last minute questions?
Yeah, I just had a small query. Can you share the papers on which you discussed your recent ideas on learning rate,
on learning
scheduling
rate?
and all those things?
Okay.
Then I can read those up.
Sure. So I'll do one thing. I'll just update the same Jamboard. I'll put it here in the links for this these two ideas. Reduce LR on plateau and this guy. Yeah.
And Selu also, some reference if possible on
Selu.
Selu.
Yeah. Okay. Okay. Well, let me just write it down somewhere. Forget.
Yeah,
So
that would be very helpful.
one thing was Selu you wanted. Second was reduce LR on plateau. And third thing was that batch size, LR versus batch size.
Yeah.
Yeah.
Okay.
Okay. Yeah. Okay. Okay. Anything else? Any other questions you guys have? No? Okay. Take it. So we'll meet again next Saturday. Sorry for taking some more time. Chalo, see you guys. Thank you.
Thanks, Raj. Nice.